Okay, we're back. I think what we would do at this point is try the next tutorial. He seems to be doing very small sections and then uploading them one at a time. I'm not entirely unhappy with that idea because it lets us experiment a little bit. In the last schematic demo, he said that he was using, I think it was the copy tool. Let's see, which one was the copy tool? Can we remember? Is it this one? This one. The one where the two guys are holding hands? Is it guys? Well, these two stick figures are holding hands. That's the copy tool. So if I click in here and then click on my little 555 timer, it should copy it, right? Yep. So there's a copy. So now I have two timers. Ooh. How slick. And we could try it again. Yep, there's another timer. So that's kind of cool. Copy tool. What else did he show us? I think there was something about define the value of an object. And here it looks like it could be the NE978 surface mount. And over in here, no user, do you want to change it anyway? Yeah, sure, why not? So now it looks like it switched down in here from M555, a $10 part, to the NTE978SM, which is a surface mount version of the 555 timer in a smaller form factor. So now if I went to find out more about the NTE978SM, I could probably type it in and maybe find it. NTE978SM, enter, and I guess I put an M in there. Let's see if that works. Yep, there it is. Integrated dual timer data sheet, and maybe I can get some images of it, see what it looks like. Yeah, it's teeny. Look at that. This nice little surface mount 555 timer, and apparently you can buy them on eBay. 14 pins means 7 pins on a side. 1, 2, 3, 4, 5, 6, 7. Yep, that looks about right. And if I wanted to go and score one on eBay, I guarantee you that no one would have the temerity to charge me $10 for an integrated circuit. The other thing that I think would be really swell is using one of these things means I don't have to have any holes because it's surface mount. And guys who assemble these things really hate holes. So what that means is you can get a little pick and place machine, get a tube full of this stuff, and just pick it in and assemble these things at high speed. So single unit quantity, looks like it's $1.55. Here's an NTE 955 SM. Suppose we could try that. Let's see, schematic, mouse right, properties. Cancel. I want to change the property on this. So that would be, let's see, here's the move tool. I'll click on the device. Then I'll, whoops, it's moving. Help! Click here. And now we'll go to here, change the property. Yes, and we'll make it an NTE955SM, because that's what I found on eBay. So we're now designing with eBay parts. This is an 8-pin surface mount device. The other thing was 14 pins. The reason this is fewer is because it's not dual. This one had two 555 timers built in. This one only has one. Maybe I only need one for my application. And in fact, if you look at the DIP version, this is identical to the DIP version except that it's in a smaller form factor and it's surface mount. So that's really what I need for manufacturing inexpensively. So now if I go back to my my schematic and click OK, yeah, it updates the name of the device, which is just fine by me. Because now if I go to design So let's try general. Oh, see, he's not going to let me. Can I paste it in without seeing it? Nah. I want to cancel. That must be cancel. I can't see. It's either search and cancel. Let's look at the schematic. See how it comes up. It's so important that we not pick $10 parts. Clicking on manual search, I click my little capacitor. Okay, I found the LED is not there. I'll do another manual search. Here's something that looks similar. I'll select that. Now let's see what we have here for a 555. Here's the NTE 955 surface mount. I don't have any. Oh wait, that's $10. Maybe because I don't have it, they just priced it at $10 to make it worth their while to order it. Because that's just bizarre. Didn't I just see this for $1.75 on eBay? Yeah, they don't have it, so they said it's $10. Well, it's clear to me that Adafruit parts are making me feel hopelessly middle class. There's just no way I should spend $10 on something I can get on eBay for $1.25. And that's unit quantity with free shipping from China. You know, if you wanted to like make 100 of these things, it's not going to cost you no dollar and a fraction. You know, it'll be pennies. Guaranteed. So let's go back to our little tutorial. And I'll start it from the beginning.
Okay, hey, this is Jason with RPC Electronics, and this is lesson 3 of the Eagle tutorial, and we're going to go ahead and dive right into it here. In this lesson, we're going to go ahead and start creating the schematic for an actual usable circuit, or an actual usable functioning circuit board. So what we're going to do is we're going to design a quick little LED circuit with a voltage regulator and a couple filtering caps. So let's go ahead and get right into our parts, and we're going to run into a couple of other tools that I didn't go over in lesson 2, and we'll go over some of those as we're doing it. So first thing we're going to do is we're going to go down to one of the things you'll learn with Eagle is the naming of libraries. You just get used to the libraries, just go through them and familiarize yourself with them. Some of the more common stuff is not exactly
Oh, downer. I'm really bummed. He's giving me the spinning beach ball of death here. Can you see that here? Yeah, what could be the problem, I wonder? We'll start it from here and just run it again.
Just go through them and familiarize yourself with them. Some of the more common stuff is not exactly jumps right out at you, and I'll try to point some of that out to you. First thing we're going to do is we're going to go to VREG for voltage regulator, and we're going to get a standard 7805. This would be a 220. A TO220 case. So once we've selected the part we want,
okay, so a TO220 case looks just like a power transistor. It's got a metal tab on the back with a hole in it, and the hole is for what they call a 632 nut and bolt. That is a number 6 screw with 32 threads per inch. And what you can do is you can bolt this onto a heatsink with a little heatsink compound. The LM series, the 7805, for example, will give you a regulated 5 volts with an unregulated up to, let's say, 9 volts input. So if you have a 9-volt battery and you throw it in there, it'll give you 5 volts out. But it comes at a cost. This is a linear regulator, and it generates quite a bit of heat when you start to draw up current. So this is one of those things where you kind of have to decide whether it's the right application for you or not. You can get regulators that'll give you fixed voltage out, you can get regulators that give you variable voltage out, and you can get some that give you fixed voltage with variable current out, depending upon what it is you want to do. For example, if you have a laser diode, they want a fixed voltage. They only operate at 1 voltage. But if you want to change the brightness, you can change the current they draw. So with a variable current regulator, you can alter the brightness of a laser diode, if that's your application.
Just double click. One thing you'll notice is when you click on a part, it's going to give you a preview here on the right. It's going to show you the emblem for the schematic as well as the footprint that would actually be on the board. So in this case, we're going to choose a 7805 voltage regulator. So we'll go and click that down, and you notice automatically it gave us a IC1. It automatically named it. Let's go ahead and give this IC a value. So we'll use our value tool that we used in lesson 2, and we're going to go ahead and put it in 7805. And when I click OK, it's going to add that. So, we need a way to get power to this, so we're going to go get a standard coaxial jack. Under the connectors, all the connectors will have, the libraries will start with con for connector. And in this case, we're going to use a jack, and we're going to use we'll use a standard power jack, and I guess we'll go with this one right here. And I'm going to go ahead, and one of the things you'll remember, or that you'll realize, is as you go, you have to make changes as you make the schematic. But if you know you're going to be adding parts in, you might as well go ahead and account for that. In this case, we're going to have 2 filtering caps. One's going to be in between this connector and the voltage regulator, as well as a cap on the output. So we'll go ahead and click this where we've got some space, and I'm going to go down to the RCL library, which is resistors, capacitors, and inductors. And whoops, I passed it. There we go, RCL, and we're going to go to capacitor US symbol, and we'll get the let's see here, this will be a good one right here. And actually go with this one. Double click on that, and I'm going to click one here, and I'm going to click one here. So it's our filtering capacitors, one for the in.
Okay, so what's a filtering capacitor do? We've got DC in and DC out. The DC in is going to be an unregulated, let's say 9 volts or 7 volts. If it's coming in with ripple on top, we'd like to filter that out. Yeah, so this is a low-pass filter, taking the ripple. Lots of things will generate ripple. If you start with an AC wall wart and it's giving you a sine wave, you can take the sine wave and run it through a bridge rectifier. But that bridge rectifier's output is going to have a whole series of little bumps on top. Run it through the low-pass filter, takes the bumps out, throws a little capacitance in there, and you want to do that on both the input and the output for the linear voltage regulator, especially if you're dealing with what's called pulsating direct current. So that'll give you the ability to charge up the capacitor and then smooth out that ripple as it discharges. Meanwhile, the regulator should make sure you have a constant 5 volts. And then its output should also be filtered if your electronics is sensitive to that kind of noise.
One for the output. Now in this case, let's go ahead and go from here, and let's go and make some connections. So we're going to go to our line tool, and first thing you're going to notice is when you click, you can, as long as you're moving your mouse around, it's going to stay connected to the pin that you first clicked, and it's not going to go away until you click. But then you see it's still connected. So if we want to stop that, we're going to go back to that point, and we're going to click one more time. Now we're released. We'll go and connect this capacitor. We're going to click once, and we're still connected, so we'll click the second time. And in this case, I'm going to take this, and I'm going to run this down to the capacitor, and then I'm going to run a line up. And you'll see why we did that here in a second. Now with these capacitors, obviously in this schematic we can tell these are connected, but one way to visually show that is to use the junction tool, which is this little dot, and we're going to take that and we're going to click once here, and we're going to click once here, and that's going to show that those capacitors are definitely connected to those points. In cases where two wires are running over top of each other and don't have a junction point, that is typically taken as there is not a connection there. And in Eagle, that is true. Okay, we'll do one last little ad here before we end up or stop this lesson, and we'll be completing it in the next lesson. One last thing we're going to do is we're going to go to the supply, and supply is going to have our voltage and grounds. In this case, I'm going to pull the 5 volt, and I'm going to click that here. Now, what that's going to do is anywhere on the schematic that we put one of those, it's going to automatically connect those all together. So in this case, if we need 5 volts to be fed into any part, we can use the same symbol, and 5 volts will always be taken to that point on that part. We need one more thing out of the supply library, and that's the ground. And we're going to click that here on this capacitor. We're going to click it here on this capacitor. And I'm also going to click one right here for the regulator. But the reason I did that is I like to keep everything in line so it's kind of aesthetically pleasing as well as functional. And then of course I'm going to use my line tool to connect the ground point to the regulator. So let's go ahead and save this schematic. I'm just going to go ahead and click save, and that saved it automatically. And we're going to go ahead and stop it from here, and we'll see you in lesson 4. Thanks a lot.
Alright, so that didn't seem too bad, I think. This is this the next one? This one, 4. Alright, let's stop it. And then what I thought I'd do is go back to my schematic over here, make something new, and then what we'll do is we'll see if we can't do some of what he had indicated. We were looking for a jack, right? And now we see there's a whole bunch of jacks, AC jacks, DC jacks, but his jack was something like a DC power jack like this one. And clearly that's available, and so that's a good time. He said he also wanted to have an LM regulator. I think it was a 7805. Now I'm not sure if we're going to be able to just type that in. We can't. So if I want a voltage regulator, I may have to do something about it. Let's see, 78XX, was that the one he used? Searching, not working. How did he find that? Voltage regulator. Oh, okay, fair enough. Positive voltage regulators. So what do we got here? 7805, but that's in a 2-3 case, right? And he was talking about putting it into a slightly different case like this one. You know, the 2-3 cases don't, you know, they look more like transistors because they don't have any metal on them. They're just plastic. They might be good for maybe, you know, quarter of an amp, no more. After that, they burn out. If you want something that can take an external heat sink, then you want the 2.5 package. That way, you got a place for your hardware. You got a piece of metal. If you can run this underwater, and I have, you can actually crank it to 1.5 amperes. After that, the thermal gradient between the inside die and the outside plastic gets too high, and it explodes like a depth charge. It's so cool. Don't try this at home. Or if you do, make a video of it. Because next time I do this, I'm going to make a video. So he tells you the description. It's in a 2220 package. I can throw it in here. Let's see, what else did he do? He threw in a couple capacitors. Did he tell us the values? He didn't. No. And he didn't tell you if they were electrolytic capacitors or ceramic capacitors, but I think they were polarized. So if I throw in capacitor, it's such a such a big thing. And there's so many capacitors. There's just here's a capacitor. What could it be? I don't know. If I want an electrolytic capacitor, that's one that's going to be polarized. So here's a polarized capacitor. And then these come in all these different surface mount flavors. They come in all kinds of through-hole flavors. He didn't really tell us much about it, did he? They come in different, you can get capacitors with different breakdown voltages, as well as different capacitance. So you can get a capacitor that's good to like 10 kilovolts, but you don't need that. So there's some compelling argument for making sure you've right-sized your component. And he didn't really tell us very much about that. So as I try and reproduce what he just showed me, I realized, hey, I got a bunch of questions. What capacitance should I be using? What working voltage should it be running at? Should it be polarized or non-polarized? Right? Some of that might be a design issue, because if you know something about the input ripple, you might be able to size the capacitor right. So a bunch of different capacitors here. I'm not seeing one that I oh, there's one. This is an electrolytic capacitor, 2 millimeters by 4 millimeters. That's little. I got to tell you, a lot of components that died on me died because their capacitors failed. Now that could be because I had undersized capacitors, but these are Apple products. I think they were designed right. Could be they were counterfeit capacitors. There's a big scandal in the industry about counterfeit capacitors coming in. And these can cause failure for a variety of reasons, most of which is the capacitors just sort of die out. And the other thing he picked was European versus US capacitors. And I find that very interesting too. What exactly is the difference between European and US capacitors? Are we measuring things in inches instead of millimeters? I see inches in here, but I also see millimeters. So I got more questions for him, and I think he did mention he was selecting for a US capacitor. And these numbers seem to indicate the outline size. Here it says 5.5 by 7.5, and he means 5.5 by 7.5 millimeters. So here's a bigger one, 13 millimeters. So I guess I could pick any outline I want. Here's a giant one. That one's like an inch. 1 inch by 1 inch by half an inch. That's a big capacitor. So when you're picking these things by form factor, you're also going to want to sit there and sort of type in the values, I should think. Let's throw in some capacitor, and then let's go back to the property in here, put in the value, 100 microfarads. Go in here, put in the value, 100 microfarads, and then we'll get the move tool, move it around a bit, get the wire tool. There should be a way to make this larger. Let's see, if I hit the control key and hit scroll, this gets bigger, so you can see it better. I should probably have done that more neatly. Twice. One more time. There. Did it. And then he said something about getting the connector tool. So we put in the junction to show the connection. And then I think he said something or other about adding the ground. Was it VSS versus VDD? I forget, or maybe it was just ground. Yeah, that looks about right. So we'll put that in there, put that in here, put that in here, and I guess we can put that there. If I get my move tool and I want to make it so that everything is aligned, I can just drag it. I don't have to add a separate wire. The wire will extend itself. And it shows the connection in here. This comes up as green. So now everything's all lined up except for this, which I think I can move to here. And didn't he do something else with VCC? VCC. Enter. So here's the supply symbol. He did what now? I'm sorry, could you say that a little louder? I'm okay? Oh, alright. Oh, I see what you're saying. He gave it a property. Oh no, it's got a property. I'm sorry, what were you saying? Something like this maybe? And he made it like 5 volts? He called it 5 VDC? 5 VDC. Is that good? And then if I go back to move, in theory I should be able to click on this, drag it around. I guess this is the part where I can just sort of add a little wire and wire it up. Yes. And now if I want to, I can add a connector, although I don't think it's necessary. And then let's see, if I go to the move tool, well, now I've got 5 volts regulated and I can put it anywhere I need it. How's that? Good, right? That's sort of what he was trying to get us to do. This is the kind of way I learn this stuff. Just watching him isn't enough. I need to be able to do it on my own. Now, if you told me, gee, that's very nice, but I want something else. I want not just 5 volts, I want, I don't know, 15 volts. Maybe the input to this is 18 volts. I don't think this is going to take 18 volts without blowing up. But I could have a separate jack. Why not take the whole thing and then copy it and move it to, oh, it's not, you can't group it all together? Darn it. It seems to me like it should be possible to group everything. Group. Where do you see that? Oh, there it is, copy group. Ah, now we're talking. So now I got a full-blown duplicate of the prior circuit. There should be like a delete tool in here so I can get rid of this extra thingy. And now I can go through and say, okay, we've got an IC3, completely separate IC. If what I really want to do is, let's see, get the move tool, mouse right, go to the properties. I should be able to change this from a 7805 to something else. Let's see now. How do I do that? Going over here, click on the regulator, change it anyway, and now if I want, I'll just say, look, I don't need 5 volts here. I need 15 volts. You know there's a 7815 as well as a 7805. So if I click that, blammo, I'm there. Two connectors, 2 regulators, and I better change this voltage out here, right? Because otherwise we're going to have 5 volts connected to 15 volts, and that's bad. So I better, knock that out, and then put in a different connector. Maybe we'll call it VCC. So I'll do another look for VCC. I'll put it down and over here, but I got to give it a different value. Let's hook it up to my no, this has to be a different network. Oops. And now we'll give it another name. Let's see, what shall we call it? How about we call it 15VDC? There. So now I've got 2 separate regulators with 2 separate power supplies. which I think is just fine. And the only thing I have as a problem is, well, I now need 2 wall warts with 2 jacks. I'm not too pleased about that, but that's okay because I need a basic redesign because I don't plan on running 20 volts into my 5-volt regulator. This is an interesting point. These 7805 regulators are available in different currents, and if you go and look at your Arduino, it runs out about a 1/4 of an amp maximum for that regulator. If you put in, I don't know, 12 volts from a car battery, because we tried to do that with the wheelchair, it blows out, I don't know, I'll say in a fraction of a second, faster than a blink of an eye, that kind of, just, it's gone. And so it doesn't like it when you over voltage it, especially when it doesn't have a heat sink. It just burns right out. So what do you think of that? Good, right? You guys can do this now, right? Regulators? It's not a particularly complicated thing, but you can see how useful it is. Everybody who builds a circuit is going to need power. Everything needs power. And the LM Series 7805 or whatever type regulators are probably the ones everybody thinks about. They're cheap, they're common, you can get them in a wide variety of different circuit form factors.
Hi, this is Jason with RPC Electronics, and this is lesson 4 of the Eagle tutorial. In lesson 3, we started this new schematic for our first real project, and I'm not going to go over everything I just did in lesson 3. If you need a little recourse or a refresher, go back.
Hey, wait a minute! He didn't hook up the ground on his coax connector, right? So this coax connector is just not hooked to anything yet. That's kind of too bad, really. Did he forget that? I'm not sure.
And watch it, and then watch this one. First thing we're going to do is a couple little housekeeping things with what we already have here on the screen. That's just a matter of some conventions and making the schematic a little easier to read, plus we have a little bit of function that we need to do. First thing we need to do is, some people might notice that we're missing a ground off of this power jack. One thing with this particular power jack is it has a self-isolating pin, pin 2. When nothing's plugged into the jack, the function is that pin 2 and 3 are tied together, and when a plug has been plugged in, pin 3 will actually disconnect from pin 2, isolating the two. So in this case, we don't need that function, so the easiest thing to do is actually tie them together, short them together, so no matter what is plugged in or unplugged, you always have a direct connection there. So first thing we're going to do is we're going to use our copy tool, and we're going to copy the ground, and we're going to come in here and we're going to pop a ground in there, and this ground is going to get tied to the jack, and we'll use our wire tool. And in the previous lesson, I believe I called this the line tool. If you hover over it, it tells you wire. If you look down the bottom left, it says draw a line, so you choose what you want to call it. I'm going to refer to it as the wire tool. We're going to click once on the ground, we're going to click once on this pin, and then we're going to click a second time on this pin, and then we're going to click again to disconnect away from, or to get the tool to release the wire. Another thing that we'll want to do, and this is just a convention thing, we know that this connection has been made because we physically did it by clicking on it. But to ensure it as well as for a visual aspect, we're going to use the junction tool again, and we're going to put a junction right there where this pin comes midway into a wire. And again, that's more of a convention, but it's also functional, as in if you want somebody to be able to look at the schematic and discern whether that pin is connected or not. So we're going to go ahead and do that. Another little housekeeping thing we're going to do is we're going to go ahead and give these capacitors values, since we didn't do that in the first lesson. And in this case, we're going to give these a value of 0.1 microfarads per cap. So that looks good. Alright, next thing we want to do is let's go ahead and add in our LED. And in this case, where Eagle can be sometimes cryptic with the naming convention, in this case, the library is actually called LED. The one thing you want to be careful though is that all these parts underneath the LED most of these are user submitted custom parts. In this case, we just want a standard T3 1/4 LED, which is going to be under this little sub LED section, and that would be the 5mm LED. So let's go ahead and click on that, and let's go ahead and put that LED in the schematic. And while we're at it, let's go ahead and get a current limiting resistor. We're going to go to the RUS, and this part right here will be a 8-watt flat laying resistor. I'll go ahead and change this so you can see that a little bit better. It's a flat laying; it'll lay flat on the PCB. So let's click OK. And another quick little tip is, anytime you need to change the orientation, you can very easily just right-click your mouse, and it will change the orientation of the part. And we're going to go ahead and add this part right now. And now what we need to do is get power to this LED as well as a ground. So let's use our copy tool again, and we'll copy our 5-volt pole. And now that I've done that, in lesson 3 we mentioned that anywhere a 5-volt point like this is added on schematic, these points are going to be all tied together. So I can have a schematic with 100 of these if I want, and if I do, they're all going to be tied to the 5-volt bus coming back to the voltage regulator. Same thing with these grounds. Even though these grounds aren't physically connected to each other on the schematic, they're all tied to the same ground, given the same ground potential. Alright, we're going to copy the ground as well while we're talking about it, and we're going to go ahead and add that to the resistor. So now we effectively have a complete schematic with a source of power, the filtering caps, the voltage regulator, the LED, and the limiting resistor. Now that we've done that, we're at a good stopping point. I'm going to explain a couple of little tools up here on the top, and these are tools you're going to use a lot. One of them, you'll notice what I just did. If I zoom out and I want to zoom back in on the schematic, I can zoom in, but I have to kind of hover my mouse in the exact place, and then I kind of have to play with it to get it to zoom so it's centered in full size. Well, they have a little tool up here. There's a magnifying glass with a little white square or a little white rectangle in it. If you click on that, it's called the fit tool. It's going to automatically fit the schematic to the screen size that you're working with. You also have a zoom in, and you also have a zoom out, and that's the magnifying glass with a plus and a minus. And those are the 3 most used tools that you're going to use when zooming and navigating. Also, I always recommend a wheel mouse. A wheel mouse makes a lot of tedious movements very easy, because you can simply hover over a specific section and zoom in or zoom out very easily. And again, if you get it zoomed to just kind of a funky position where you can't quite get it the way you want it, just click that fit tool and it's going to put it right back where it belongs. So we're going to go and stop here, and in the next lesson we're going to add a couple things to this schematic. And once we're happy with the way the schematic is, then we're going to go ahead and start laying out our first board. So thanks for watching, and we'll see you in lesson 5.
Alright, so here's lesson 5. What I'm going to do is just sort of modify my little schematic here so I'm consistent with what he's done. I'll use my wire tool, and I'll hook up the disconnect, then I'll add my own little, here, I'll zoom in the way he said, and then I'll put in the little wire doodads. And what else do I need to do? Oh, right. And he also said you have to make this 0.1 microfarad, so I was off. I'm not sure why it's 0.1 and not the other, but there it is. Well, 0.1 microfarad. How's that? Did he said U for micro? Apply. Okay. And property. Oh, I can't do that. Click. 0.1 UF. Okay. Millifarad. MFD is the way I do microfarad in English, but he does U. That probably works too. Yeah, I think you did. I think you're right. So, yeah, what happened to the... Oh, there it is. It didn't show up until I zoomed in. Yeah, this is sort of weird. So that's it. What else? Did I make... Oh, right. He put in a resistor. So we want to get a resistor. Let's join the resistance. And an LED. Now, he said something or other about the resistor, right? Like its value. I think he said it was a 5 millimeter resistor. But then he said it was a lay flat style resistor. How would you know if one of these is a lay flat resistor or not? See, now this is a surface mount resistor. I don't think he used a surface mount. I think he used a through hole. I think he used a through hole LED as well. But you can get LED surface mount. You see them on the Arduinos. So, does it matter? Well, you know, if you're going to manufacture. Now he said something about right-clicking and it rotates, and that seems to work okay. And then he was going to add an LED, and he didn't exactly tell me which one. LED, enter. Oh, that was what was 5 millimeter? Okay. So within the 5 millimeter LED world, what do we got? It's a chip LED. That's the kind that I think you could do with a pick and place machine. So I'll change my I guess he went in like this, right? And he put in the 5 volts. So let's get that copy tool in there. Copy the 5 volts. Put that up here. And then we'll get the ground. Copy the ground. Put that over here. So I guess that's it. More or less. What do you think? I made this surface mount, but this is through hole, right? Why did I make it through hole? Well, because you're going to need a heatsink on it. You're going to have to do something, so you want it to stand up while off the board, and then you want to throw the heatsink on. That's going to take a whole bunch of mechanical torque and put it on the leads. So if you get through hole, it's going to have nice thick metal leads. That may help support your heatsink somewhat. Maybe it's just a design preference. Also, because I got a whole big tube of these things. You know, once you have 1,000 of something or so, then you're like, oh, let's design with that. Which is not a particularly good reason. It's just a reason.
Alright, hi, it's Jason with RPC Electronics again, and lesson 5 of the Eagle tutorial. And hopefully you've been watching these in succession, so as we're building on this project, it's making more and more sense. That's the best way to do it, is to start with the beginning, because we are obviously building on it. This lesson is going to be kind of short, because I basically just wanted to add a part, show you how to modify a schematic by adding a part, and then we're going to stop this lesson, and then the next lesson we're going to start on the basic board layout. So the only thing really we need to add to this particular schematic is I would like to add a switch. And I find that in this particular case, we're going to want to put a switch to control power to the regulator. We don't want the regulator constantly drawing power, so we want to basically cut it off. And we'll actually add 2 parts to this schematic. We'll add a diode as well as a switch. We'll put the diode in for reverse polarization. And that basically protects you from hooking it up backwards and blowing out the regulator or the LED. So,
yeah, I don't know if you're familiar with the term wall wart, but wall warts are generally wall transformers, and what they give you is a DC connector. And the DC connectors come in 2 flavors. The male is what's called the plug, and the female is what's called the jack. And what you do is you put the plug into the jack. Now in the center of the plug you can have a conductor which is either positive or negative depending upon the convention for your wall wart. And if you plug it in and it's backwards, you basically hook plus to minus and minus to plus, and that can blow everything up. So what he's suggesting is to protect the circuit from getting blown up by somebody plugging something in that isn't right, he's going to throw in the diode. That'll give you the reverse voltage protection.
First thing we'll do, the easiest thing I found to whenever you need to add a part in line is go ahead and use your delete tool, which is this this X here. I'm going to delete this this wire right here, and we need to make a little room. So I'm going to highlight everything by using these what they call the group tool. And then we're going to click the move tool, and then the trick was, if you remember from, I believe it was lesson 2, right click and do a move group. Now we're going to move that entire group over, and we'll move it over right about there, and that'll give us some room to work here. So first thing we want to do is go ahead and grab our diode. So bring up the libraries here, and sometimes when you first open Eagle, it takes a few seconds to read in all the libraries. There we go. And we're going to go down to the diode library, and the diode library is like the LED library, where it actually is named what you're looking for, but a lot of these parts in here are going to be user-defined parts, and a lot of them are going to be specific to certain parts. And in this case, we want to go to just the diode subsection. And as you go through here, you're going to see that there's many choices. And we're just going to go with a basic diode layout here. We'll go with this one.
Okay, in my view, the hardest thing is knowing which part to pick. You've got so much choice, and if you pick the wrong part and you start designing everything through hole, and then you realize, oh, I'd like to go surface mount, it's a big deal, because now you've got to go back and redo all the parts. So and I was thinking about this as a homework. You guys have already done the schematic layout for a surface mount style through hole 555 timer. What would happen if I said, now let's do it again, only this time let's make it through hole, like the one you see here in front of you. So it is the case that you'd have to do quite a bit of work, but you could keep the schematic. But you'd have to change all the parts, and that's the key. And then, of course, layout may change as well. In fact, I think it almost certainly would. So just going from surface mount back to through hole, that's not particularly easy. And I don't know if you noticed, but my entire board is made single-sided. Single-sided boards are particularly challenging, but also very rewarding because we can fabricate them right here. So what that means is if you need a via, because some two wires have crossed, you can substitute something like a resistor or a capacitor, and that'll serve as the bridge, so you don't actually have to add a wire jumper. So these are kind of interesting ideas, right? If you go from surface mount to through hole, a lot of redesign involved.
And we're going to go ahead and click this and add it in, and then we'll use our wire tool, and let's go and connect that diode. Next thing we'll do is grab a switch, and you'll find that there are many libraries for switches. In this case, we're going to go with the Omron switch. Omron, these are just some switches that I use a lot. And they've got many flavors of switches. In this case, I'm just going to use this. And here we have a good opportunity to show you a trick. If I rotate this switch, I can do it in obviously in any of these four directions. In this case, we're going to just go ahead and add in right here. Well, it's not really a trick per se, but we can turn that either way. We can even use the mirror tool to turn the switch around. So now it's actually essentially backwards, but we're not going to worry about that in this case. And we're going to use our wire tool, and we're going to connect it into the schematic, or into the circuit, I should say. And let's go and use our junction tool, and we'll junction those. Now, you may be wondering why I connected these together. These two pins are actually connected internally in this particular switch, but it's not always the case, and sometimes you want them to tie it together. And in this particular case, because I know what type of switch we're using, I went ahead and tied them together anyways. And let's go and zoom out to take a look at, and always save often, just in case. So here's our completed schematic, our completed circuit. And in lesson 6, the next lesson, we're going to take this and we are going to create our very first board. So that's it for this one, and we'll see you in lesson 6. Thanks a lot.
Well, I think by now we've kind of had our fill with Eagle schematics, but maybe it was good to have a little thoroughness behind the lectures. I really like the idea of kind of going through the detail and seeing everything. I even like the idea of sort of trying it here in front of the class, just to make sure that we have a good understanding of it. So what I would do is I would try and duplicate what he just did. And I don't know if you noticed, but he said let's save it often, so I'll do a save as well. And I'll give it a place to put, let's see, how about this? We'll call it LM7805, and maybe we could give it a folder, huh? Doesn't seem to have... Can you make a new folder here? New folder 7805, enter, double click, and save. So now I got a place for it. Hadn't thought about saving it until he mentioned that you should save often, and then I said, gee, I haven't saved at all. And then there was another thing he said, and I thought that was pretty good. He said that if you take these things and then mouse right, you can move group, but I don't see that here. Mouse right, copy group. No, I want move group. Oh, here it is, move group. Whoa! How did it decide what the group was going to be? Move group. Oh, that works. Okay, so that sort of works. Let's try another one. He said he wanted a diode, right? So, anybody remember which diode he selected? This one looks like it can handle about 4 amperes. This one's got through hole. I suppose that's okay. Here's a surface mount diode. Can throw that in there. Why it didn't appear, I don't know. There it goes. And then he said something about a switch, right? So what did he pick for a switch? An Omicron? I'm not seeing it. Yeah, Omicron's not showing up for me. Oh, here it is. Omicron switch. Apparently that's an Ada Fruit Library thing. So we'll throw that in there. And then we'll move this over. Make a little room for our diode. Just put that in there. A little room for the switch. And we wire it up. Whoops. I got it all messed up. Just a minute. Yeah, that's not quite right. Let's see if we can fix this. There. That's better. And what about this wire? Done. Good enough. And save often. Are we out of time for today? This class ends at what, 1:30? 1:30. Alright, so for next week, I'm thinking that you guys can follow this tutorial. You should be able to submit a voltage regulator. That shouldn't be too much difficulty, so you're kind of doing what I just did in the class, getting used to Eagle, doing a schematic layout. And what we'll do is we'll follow this up by bookmarking it. So let's see. Bookmark. How does one add a bookmark? Control D. Done. So now I've got a little bookmark. We can finish this up for next time. And what we'll do, I think you should, yeah, let's go up to this point, and we'll finish things up a little bit later. So let's go to Axiom Mentor. We'll do a message, and let's write it up just so that people can see it who aren't here. And what we'll say is something like subject homework 2, is it? And using the tutorial in class at, and I'll just push this in here, do the LM 7805 schematic and upload to Axiom, X-I-O-M. And I should probably have turned it into a proper homework, right? Cut. Let's go back. Assignments. Create new assignment. Homework. Title. Homework 2. Wait 1. Save and edit. Do. Yes. I should have done. Maybe I didn't. Display grades on. Let's see. Submit URL, no. Online submit, yes. What else do I need to do here? Paste. Using the tutorial in class at here. Do the LM7805 schematic and upload to Axiom using Eagle. And I hit save. The assignment will be hidden. Why will it be hidden? Oh, and now what about the grades? You want to? The grades are on, so I hit save. And then for the last one, I can do edit. No. Display. I'm losing it. On. Save. Okay? Are we good? Alright, thanks a bunch, guys.